Ever thought about the sheer scale of data centers? I mean, these massive hubs handle almost unimaginable amounts of information.
It's staggering, really.
And then you start wondering about securing all that traffic, right?
Mm.
Encrypting it without bogging everything down.
Yeah, that's the million-dollar question, or maybe billion-dollar at this scale.
Okay, let's unpack this because today we're taking a fascinating plunge into a solution from the engineers at Google.
We're looking at a security protocol they call PSP, PSP Security Protocol.
And we're going straight to the source.
Exactly. We've got their public specification document, the nuts and bolts.
Right, no marketing fluff here. Our goal today, and you're listening, so you're with us on this, is to really understand why Google developed PSP.
And crucially, the clever architectural choices they made. How they secure this immense traffic within their data centers.
Think of it as getting the inside scoop on some serious networking innovation. We're digging into a technical specification, so yeah, expect some real details.
Definitely. So at its heart, PSP is Google's way of tackling that challenge. Keeping data safe as it moves around inside their, massive data center networks.
It's a security protocol built specifically for the demands of that environment. Encryption in transit.
Right. And here's an interesting point. Google has made PSP open source.
Oh, really? So they're not keeping this just for themselves?
Nope. They're hoping others will find it useful, maybe adopt it more widely.
Which, if you're like us, trying to quickly grasp a complex area is a real plus. A well-documented, potentially widespread solution is always good.
Absolutely. Okay, so to get our heads around PSP, we need to understand a fundamental idea: security associations. S for short.
It says, okay.
Think of an SA as a secret agreement between two devices. It defines how they'll secure their conversation.
Like having a unique code book. And encryption rules, just for them, for that specific data flow.
Pretty much. Specific crypto settings, keys, IVs, that sort of thing.
Okay, so one secret agreement for each data exchange. That sounds like it could add up to a lot of agreements to manage.
It definitely can. And a key thing to remember, in PSP, these agreements are one-way, unidirectional.
One way only. So for a typical back and forth, like a video call or something.
You'd need at least two SAs, one for the data going in each direction.
Right, makes sense. One for sending, one for receiving.
Yeah.
But here's where it gets, really interesting.
Mm-hmm.
The specification emphasizes that PSP is designed to handle a huge number of these SAs without needing dedicated hardware resources for each one in the network interface card, the NIC.
Ah, yes. That's crucial. No per se hardware state in the NIC, and that sounds like a major hurdle to overcome for massive scale.
It really does. Which leads us directly to a core innovation of PSP.
Receive side key derivation.
Exactly. This is where PSP really shines, in terms of handling enormous scale.
So the NIC on the receiving end, it doesn't need this massive inventory of decryption keys stored for every single SA.
Correct. Instead, it can figure out the right decryption key for an incoming packet, pretty much on the fly.
Like a magic decoder ring.
Huh? Well, probably more like some very clever engineering. How does it do that?
It uses information that's actually in the received packet itself. That, plus a secret that's kept securely inside the NIC.
Okay, so it's not looking up a stored key for that specific connection.
No. Which is a big departure from older methods, where the NIC would often need to maintain per SA state, storing the specific key, other details for every active connection.
So instead of the NIC having this huge phone book of keys, it has a secret recipe. It generates the correct key when it sees a particular packet arrive.
You got it.
That must save a tremendous amount of memory on the NIC.
Oh, absolutely.
Yeah.
The core insight here is Google's ingenious way to bypass that traditional NIC memory bottleneck. It allows for, unprecedented scaling of secure connections without needing super expensive hardware upgrades.
The specification even gives a potential example, right?
It does. For, say, 10 million connections, the memory savings could be around 2.5 gigabytes of DRAM on the NIC itself.
Wow. 2.5 gigs. In a world where memory on network cards is, really valuable real estate.
Yeah, that's a significant win. A very big deal.
Okay, wow, that's not pocket change. But the document also mentions an alternative, maintaining per SA hardware state.
Right. That is an option.
Why might someone choose that route if receive-side derivation is so memory efficient?
Well, it boils down to a trade-off, mostly packet rate, how fast you can process packets. While receive-side derivation lets you handle a huge number of connections without running out of memory, keeping per SA hardware state could potentially lead to a higher raw number of packets processed per second. In some setups, anyway.
So faster key lookup, because it's already stored.
Potentially, yes. It's a question of whether that faster lookup outweighs the memory cost and the overhead of managing all that state versus deriving the key for every packet.
Interesting. So it's a choice. Massive connection count versus maybe squeezing out every last bit of packet processing speed. Okay, moving on. The spec talks about different operational modes.
Yep.
Or versions of PSP.
Right, two main ones.
What are the main types we should know about?
There's one using AES GCM. That gives you both encryption, keeping the data secret, and authentication, making sure it hasn't been tampered with.
Encryption and authentication. Got it. And the other?
The other uses AES GMS. That offers only authentication. No encryption, so the data isn't secret, but you know it's genuine.
Okay. Privacy and integrity, or just integrity. And the spec points out something about what PSP authenticates.
Yeah, this is important. It authenticates from its own header onwards. It doesn't look at the outer IP or UDP headers.
Why is that significant?
Flexibility. By focusing on its own internal structure, PSP can be used in different network scenarios. Right now, it's inside UDP packets. But they mention the possibility of it being directly within IPv6 packets later. The authentication isn't tied to those outer layers.
So it's more adaptable. Makes sense. Now, when talking about the AES GCM mode, the one with encryption, the concept of a crypt offset comes up. What exactly is that?
The crypt offset is quite a clever feature. It lets you specify how many bytes at the beginning of the main PSP data after the initial setup info should remain unencrypted. Plain text.
So part of the payload stays clear.
Right. While the rest is encrypted. But here's the key part. Even the unencrypted section within the PSP frame is still protected by the authentication.
Oh, interesting. So you could have parts of the packet that are in plain sight, readable, but you're still guaranteed they haven't been messed with. What's the practical benefit there?
This enables some really useful things. For instance, you could leave header information inside the PSP payload, maybe things like TCP or UDP ports unencrypted.
Okay. So why do that?
Well, it allows network devices between the sender and receiver, like firewalls or load balancers, to make decisions without needing to decrypt the whole packet.
So a firewall could check the ports to allow or block traffic.
Exactly. Or a load balancer could use that info to distribute traffic effectively. It also opens up possibilities for richer network monitoring, looking at samples of traffic without full decryption.
That's pretty smart. Selective encryption, but with a full guarantee of integrity. Okay, so we've covered what PSP is, sort of the basics. Now let's get to the why.
Right. Why did Google go to the effort of creating a whole new protocol?
The specification lays out three main advantages: simplicity, improved functionality, and increased scalability. Let's start with simplicity. How does PSP achieve that?
Simplicity comes in a couple of ways. First, PSP focuses on a streamlined set of features. It concentrates on what's most important for these large-scale data centers.
Less is more kind of thing.
Sort of. It means things like a simpler approach to replay protection. Instead of complex network-level stuff, it relies on the protocols running on top of PSP, like TCP, to handle that.
Okay, pushes that responsibility up the stack.
Right. They've also removed IP6 authentication header, AH, and they chose a very small number of strong, well-vetted crypto algorithms, mainly AES 128-GCM and AES 2506 GCM.
Fewer moving parts, fewer options to configure.
Yeah, that definitely sounds simpler.
And then there's how the data is packaged up the encapsulation format. How has that been simplified?
They've made some smart choices there, too. The next header field, which tells you what kind of data comes after PSP, is right at the beginning. Makes it easier for hardware to parse quickly.
Cool.
They added a header extension length field, again, simplifying processing. The initialization vector, or the random value used with encryption, it's always included. Mandatory.
Always there.
Yeah. And they've done away with a separate sequence number. They rely on the IV always increasing, which serves a similar purpose.
So it sounds like they really thought about making it easier for network hardware, for the NICs, to process these PSP packets efficiently. Okay, makes sense. Now on to improved functionality. What new capabilities does PSP offer?
A key improvement is the mandatory use of UDP encapsulation.
Mandatory UDP.
Right.
Was that an improvement? IPsec can run over UDP too, right? Using UDP encapsulation like RFC 3948 describes.
It can, yes, but it's often optional. PSP requires it. And this lets them do something clever with the UDP source port.
What do they do with it?
They put information derived from the inner headers, specifically a flow hash, into that UDP source port field.
A hash of the inner packet details in the outer UDP header. Why?
Load balancing. Network switches can look at that UDP source port when they're deciding how to spread traffic across multiple paths using techniques like ECMP or WCMP routing.
Ah. So the switches don't need to look deep inside the encrypted packet. They just look at the UDP source port provided by PSP.
Exactly. It helps them use all the available network capacity much more effectively, distributing flows better. It's about leveraging the existing network infrastructure smartly.
That's clever, exposing just enough internal info to help the network route traffic intelligently. The spec also mentions the flexible crypt offset, again under improved functionality.
Right, we touched on that. That ability to have part of the data in the clear but still authenticated, the AEAD capability. It allows intermediate devices like firewalls and monitoring systems to inspect relevant parts without full decryption.
Still seems really useful.
And one more thing here, the way they generate the IV using a precise timestamp, which we'll dig into more later, it opens up the potential for measuring network transit time, packet latency.
Oh, interesting. So maybe for network performance monitoring down the line. Okay, finally, the big one. Increased scalability.
This is really PSP's headline feature, I think.
We've already talked about the receive-side key derivation saving NIC memory. What else contributes to better scalability?
Well, that lack of per-assay state in the NIC hardware is the biggest factor, as we discussed. It immediately lifts the limits on the sheer number of secure connections that are imposed by the NIC's own resources, like its memory.
So the NIC isn't the bottleneck for connection count anymore.
Right. And similarly, the speed at which new secure connections can be set up isn't slowed down by the NIC having to physically insert or delete security rules in its hardware tables.
Less management overhead on the NIC.
Yeah, exactly. And all this leads to simpler NIC designs, potentially cheaper NICs too.
The spec throws out some pretty impressive numbers here. It mentions a single server in a large data center.
Yeah.
Can have tens of millions of secure connections and handle hundreds of thousands of connection setups per second.
Whoa. Trying to manage per connection state at that scale in hardware? That sounds incredibly complex and expensive.
Right. It absolutely is. And like the spec points out, the memory savings alone from not storing all those decryption keys, potentially gigabytes of DRAM per NIC.
It's a huge advantage. By offloading that key calculation, the NIC's resources can do other things. This ability to scale efficiently is only going to get more critical as network speeds keep climbing and connection counts explode.
The document even suggests that because PSP might be easier to implement in hardware compared to something like TLS offload, it could unlock new performance possibilities.
It's definitely geared towards high-performance, high-scale environments.
Okay, we've covered the what and the why. Let's dig deeper into the architecture itself now. The spec gets pretty detailed about security associations, the SAs.
Right. We know they define how packets are treated.
But what else is important about them? How fine-grained are they?
The level of detail or granularity can vary quite a bit. An SA could be tied to something very specific, like a single TCP connection between two processes.
Okay, very narrow.
Or it could be broader, like it could cover all traffic between two virtual machines acting like a secure tunnel.
So flexible. What are the key settings defined within an SA?
Key parameters include the SPI, the Security Parameters Index. That's the unique identifier.
The tag for the connection.
Yep. Then the encryption key, remembering that the sender stores it, but the receiver derives it.
Right, the receive-side derivation magic.
Then the crypt offset we talked about. Optional settings for traffic flow confidentiality, or TFC, which is about hiding traffic patterns. And finally, the SA lifetime, how long it's valid before needing renewal.
Okay, so the STIs, like that unique ID tag on every secured flow, helps the receiver quickly find the right rulebook, the SA to use.
Exactly.
And we've mentioned how the key is calculated, not stored, on the receiver side. Let's get into that process a bit more. How exactly are those decryption keys derived?
Okay, this is where that secret formula comes in. Each NIC that supports PSP has two secret 256-bit AES keys. They call them master keys.
Master keys, okay.
Think of these as the ultimate keys. They unlock the ability to create all the per-connection keys needed.
And they're kept super secure.
Absolutely. These master keys are never shared with the main computer, the host OS, or with other NICs. They're kept ephemerally, securely in the NIC's own on-chip RAM, protected from access.
Sounds like they're taking key security very seriously. Two master keys, why two? Is it for backup?
Not exactly backup, it's for rotation. One is designated as active. All new requests for encryption keys are derived using this active key.
Okay, the current one.
The other key is in a rotated state. It was the previously active one. After the active key has been used for a while, typically around 24 hours, or if its SPI space runs low, the rotated key becomes the new active key.
And the old active one?
The old active key stays in place for a bit longer in that rotated state. This allows ongoing connections that were using it to continue being decrypted.
So you don't break existing connections immediately.
Right. Only after those older connections naturally expire or get rekeyed is the old key fully replaced. They call this process double rotation. It's a system of rolling keys to maintain security over time and manage transitions smoothly.
A rolling system.
Yeah.
Okay, and how does the receiver know which of those two master keys to use to calculate the decryption key for a specific incoming packet?
Clever bit here. It uses the SPI itself. The highest bit, the most significant bit of the 32-bit SPI in the received packet acts as a switch.
Like a flag.
Exactly. If that bit is 0, it tells the receiver's derivation logic, use the first master key, which they call master key nillo. If the bit is 1, it says use the second master key 1.
And the sender doesn't know the actual master keys, just which slot was used.
Correct. And because only the receiver knows the master keys and manages the SPI allocation, the receiver is the one responsible for choosing the SPI, and thus, implicitly, the master key, during the initial connection setup or rekeying.
That makes sense. The receiver essentially tells the sender, use this SPI. Encrypt your traffic with the key derived using the master key I've associated with this SPI.
Precisely. And to prevent using the same derived key for too long or running out of SPI bits associated with one master key, SPIs can't be reused until the associated master key has been fully rotated out.
And the NIC's firmware handles generating and managing these SPIs. The host computer doesn't just pick one.
Correct. The host requests an SA, but the NIC generates the SPI to ensure proper management, avoid conflicts, and tie it correctly to the current master key state.
Got it. And PSP supports both AES GCM 128.
That's version 0 of the protocol.
And the stronger AES GCM 256.
Which is version 1.
Okay, let's talk about the standards behind this key calculation. The spec mentions FIPS 142 compliance.
Yes, that's a common U.S. government security standard. It means the cryptographic implementations have to meet certain requirements.
So to ensure strong security, Google relies on well-vetted cryptographic standards for the key generation. NIST specifications are mentioned. Guarantees a robust, trustworthy process.
Exactly. The key derivation function, the KDF, needs to meet those standards. It has to generate the 128-bit or 256-bit session keys starting from those 256-bit master keys. And those master keys themselves are assumed to be created using strong random number generation.
And the spec gets quite technical about how this KDS is implemented. It mentions NIST SP 800-108 and SP 838B. Can you simplify what those are?
Sure. In essence, they're using established, trusted cryptographic recipes. NIST SP 800-108 defines a standard way to derive new keys from existing secret keys. It's a framework for key derivation functions.
Okay, a standard recipe book for making keys.
Kind of. And SP 838B specifies a particular tool called CM using AES 256, which PSP uses as the core engine, or pseudorandom function, PRF, within that KDF recipe.
So standard, well-reviewed crypto building blocks.
Good.
And the input to this key-making process includes several pieces: a counter, a label, a context, and a length.
Right. Those are inputs to the standard KDF.
What do they represent here?
The counter is used if they need to generate more key bits than one go-round provides might be needed for the 256-bit keys. The label is a short string identifying which PSP version the key is for, like PV0 or PV1.
Tells it which protocol version.
The context is primarily the SPI itself. Remember, the high bit of the SPI also implicitly tells the derivation which master key to use. And the length field just specifies whether the output should be 128 bits or 256 bits long.
Gotcha. All these pieces are bundled together in a specific format and fed into the KDF engine.
And out pops the specific AES GCME key for that SPI. The spec even provides examples showing the exact inputs for different SPIs and versions using the master keys K0 and K1. Very detailed if you want to implement it.
Now, a really crucial aspect of any stream cipher mode like AES GCM is the initialization vector, the IV.
Absolutely critical.
The spec emphasizes that the IV must never be repeated for the same key. How does PSP ensure ID uniqueness? This sounds vital.
It is. They rely on the NIC having a very precise clock, a 64-bit counter that measures time in picoseconds.
Picoseconds. trillionths of a second.
That's the one. Incredibly precise. When sending a packet, the NIC combines the current value of this picosecond timestamp with the 32-bit SPI for that connection.
Timestamp plus SPI.
To create a 96-bit IV. Because the timestamp is always increasing at such a fine granularity, this method guarantees that each packet sent with a given SA, and thus the same key, will have a unique and strictly increasing IV during the lifetime of that SA.
Wow. That's a strong guarantee. And on the receiving end?
The NIC also passes this IV along with the decrypted data up to the host software. It might be useful for other things, potentially.
So the IV is essentially timestamp plus connection ID, making sure it's never reused. Now, given how vital unique IVs are, what does this mean for how long an SA and those master keys can be used? There must be limits.
There are. Because IVs must be unique, and they're derived partly from a timestamp, the lifespan of an SA is inherently limited. Eventually, you'd theoretically wrap the timestamp bits or just use up the practical lifetime.
And the SPI space itself is limited too, right? 31 usable bits per master key.
Right. So to manage all this and to further bolster security, the master keys themselves have that limited lifetime we discussed. The spec mentions a typical rotation period of about a day, 24 hours.
We touched on key rotation earlier. Daily rotation. So when a key is rotated, new SIs won't use it, but existing ones might still be active for a while using the rotated key state.
Correct.
And that double rotation is needed to fully retire a key. What happens to the connection still using a key that's now in the rotated state?
Those connections need to be rekeyed, meaning they have to establish new SIs using the currently active master key.
Ah, so the software layers above PSP need to handle that rekeying process.
Yes. The details of how that rekeying happens aren't in this particular PSP specification, but it's a necessary step triggered by master key rotation. The spec also does a quick calculation. Based on the 31-bit usable SPI space and the 24-hour rotation, finding the maximum average rate SPIs can be consumed. It comes out to something like 24,855 SPIs per second. Gives you an idea of the scale they're designing for.
That's a lot of new connections or rekeys per second. And what about getting rid of a specific key that might have been compromised? Can you just revoke one SA's key?
No, PSP relies solely on this master key rotation process for invalidating keys.
Right.
There's no mechanism described for individually revoking a specific derived session key short of rotating the master key it came from.
Okay, rotation is the only invalidation tool. Makes sense for simplicity, maybe?
Yeah.
Finally, on keys. Where do these all-important master keys come from initially? How are they generated?
The NIC firmware is responsible for generating them. And to make sure they are truly unpredictable, the spec requires the NIC to include a true random number generator, a TRNG.
Hardware-based randomness, good.
Yes, as a source of high-quality entropy for creating those master keys.
Okay, we've covered key generation, derivation, rotation, lifetimes. One last security point before we look at the packet format. Replay protection. Does PSP handle that itself?
Interestingly, no. The specification is very clear on this. PSP does not provide replay protection.
Really? Why not?
It relies on protocols running at a higher layer, layer 4, the transport layer, to handle it.
Right.
For example, TCP has mechanisms like PAWS protect against rept sequences, combined with randomized initial sequence numbers, ISNs. Those help prevent attackers from successfully replaying old captured TCP segments.
So PSP expects TCP or whatever protocols running inside it to do that job.
Exactly. Other transport protocols using PSP would need to implement their own similar anti-replay mechanisms. PSP itself focuses just on confidentiality, encryption, and integrity authentication.
Okay, so it simplifies its own job by leaving replay defense to the layers above. Makes sense in a layered model. Now let's switch gears. Let's talk about how these PSP packets actually look on a wire, the wire formats.
Right. The spec mentions that currently PSP is encapsulated, meaning it's put inside UDP packets.
UDP first. Okay.
Yes, that's the standard way right now. So the order you see on the network is the outer IP header with source and destination IP addresses, then the UDP header, then the PSP header itself.
Followed by?
Followed by the actual data being protected, the PST payload. And finally, at the very end, the PSP trailer, which contains the integrity checksum value, the ICV.
Outer IP, UDP, PSP header, PSP payload, PSP trailer.
Got it. And the UDP header has some specific uses in PSP, you mentioned.
It does. It always uses UDP destination port 1000. That's how devices recognize PSP traffic.
Port 1000, easy enough. But the source port was the interesting one.
Exactly. The UDP source port is used to carry that flow hash value we discussed earlier, derived from looking at the inner packet details.
And help with load balancing by switches. Precisely. Allows switches using ECMP-WCMP to distribute traffic better without deep inspection. The spec also mentions different ways the source port value can be generated, maybe looked up in a table, calculated by host software, or even done by logic within the NIC itself.
Flexible options there. Any other UDP header details?
Importantly, PSP implementations must support sending and receiving packets with the UDP checksum field set to 0.
Checksum 0. Why?
Often done in data centers to save CPU cycles, as link layer checks provide strong guarantees anyway. But they also say supporting a valid UDP checksum is optional but allowed.
Okay. Now let's break down the PSP header itself, specifically version 0, the mandatory AES GCM 128.1. What are the key fields inside that header?
Okay, first up is next header, an 8-bit field. It tells you what kind of data comes immediately after the PSP header and its extensions. Could be TCP, protocol number 6, UDP 17, or even another IP header, 4 or 41 if you're doing tunneling.
Tells you what's inside. Got it.
Then there's HGRX-LEN, header extension length. This 8-bit field tells you the length of any optional header extensions that might follow the main header, measured in 8 byte units. This is where things like the virtualization cookie would live.
Okay. Length of extra header bits, then some reserved bits.
2 reserved bits are set to 0 for now. Then we hit the crypt offset again.
Right, the selective encryption field.
Yes, the 6-bit crypt offset, measured in units of 4-byte words. It indicates where the encrypted part of the payload starts relative to the end of the IV field. Crucial for that AEAD capability.
We discussed its benefits for firewalls and monitoring.
Exactly. The spec clarifies some rules. In AES GCM mode, the encrypted part can be empty if the offset points past the end, but you can't make it have a negative length. And in AES GM node, authentication only, this field isn't used and must be 0.
Got it. Then there are 2 single bits, S and D.
Right. S is for sample at receiver, D is for drop after sampling. These are opaque bits. They don't affect PSP's core security processing, but they can be signals to downstream devices on the receive path. Maybe instructions for network monitoring or policy enforcement.
For other devices.
Yeah.
Okay, next up is the version field.
A 4-bit field. This identifies which version and mode of PSP is being used.
We listed them before. 0 is AES GCM 128.
1 is AES GCM 256.
2 is AES GCM 128. 3 is AES GMs 256.
Right. And support for version 0 is mandatory.
And version 1, AES GCM 256, is highly recommended. The GMD modes are optional.
Correct. Following the version is a single bit, V.
V4.
Virtualization cookie present. If this bit is 1, it means the optional 64-bit virtualization cookie field is included in the header extensions. If 0, it's not there.
Simple flag. Okay. Then comes the big one.
The 32-bit security parameters index, the SPI, with that all-important high-order bit selecting the master key, 0 for P0, 1 for K1. The lower 31 bits identify the specific SA, and the spec notes these lower 31 bits must not be all 0.
So SPI 0 is invalid. Good to know. After the SPI.
The 64-bit initialization vector, the WAFI, that unique value per packet generated using the timestamp counter.
Okay. And if the V bit was set.
Then the optional 64-bit virtualization cookie field follows the IV. This could carry things like a virtual network identifier, VNI, or other virtualization-related data.
So header. Next header, XLEN, crypt offset, version, SPI, IV, optional cookie. Got it. And the PSP trailer.
Much simpler. It just contains the 128-bit integrity checksum value, the ICV.
Which is the output of the AES GCM authentication part.
Exactly. It's the authentication tag calculated over the entire PSP header, starting from next header, and the PSP payload data, both clear text and ciphertext parts, as defined by the crypt offset. Verifies nothing was changed.
Okay. Now the spec briefly touches on transport mode versus tunnel mode again. Can you recap the difference in the context of PSP structure?
Sure. In transport mode, the PSP payload, the data being protected, is typically just the layer 4 packet, like a TCP segment or UDP datagram. It's usually used for securing host-to-host communication directly.
Securing the application's data.
Right. In tunnel mode, the PSP payload is the entire original IP packet, including its own IP headers. PSP essentially wraps the whole packet. This is more common for creating secure connections between gateways or networks like VPNs, or securing traffic between virtual machines where you want to preserve the original packet structure inside.
Creating a secure pipe for packets.
Exactly. But in both modes with PSP's current definition, the whole thing, PSP header, payload, trailer, is then usually encapsulated within an outer UDP IP header for transport across the network. And the authentication covers the PSP header and payload, while encryption covers the part specified by the crypt offset.
Okay, transport secures the conversation, tunnel secures the pipe. Got it. Now let's talk about how the NIC, the network card, actually processes these PSP packets.
Oh, my.
The spec has high-level diagrams for transmit and receive paths.
Right, block diagrams showing the flow.
Can you give us a quick summary of the transmit side, sending a packet out?
Okay, sending. First, the NIC's egress logic needs to figure out the SA details, find the right key, SPI, crypt offset, etc. This might involve a lookup or getting the key provided with the packet data itself. It then builds the PSP header and the outer UDP IP headers.
It's the setup info.
Then, a part called the splitter uses the crypt offset value to separate the part of the payload that needs encryption from the part that stays clear text but still needs authentication.
Splits based on the offset.
Meanwhile, the IV generator creates the unique 96-bit high V using the timestamp and SPI. Then the core AES GCM engine takes the key, the IV, the payload data split appropriately, and the PSP header. It performs the encryption on the designated part and calculates the authentication tag, the ICV, over everything.
Encryption generates the tag.
Finally, a merge step puts the outer headers, PSP header, the possibly partly encrypted payload, and the ICV trailer all back together into the final packet ready to go out on the wire.
Sounds like a well-defined pipeline. Split, encrypt, authenticate, merge. What about receiving a PSP packet coming in?
Okay, receive side. First, an ingress classifier identifies an incoming packet as being PSP, probably by looking for UDP port 1000, and figures out where the PSP header starts after the outer headers.
Finds the PSP part.
Then another splitter module uses fields like the HDR XLEN encrypt offset from the PSP header to separate out the clear text part of the payload, the encrypted part, the PSP header itself, the received ICV trailer, the SPI, and the 5.
Deconstructs the packet based on the header info.
Now the crucial part, the decryption key derivation unit takes the received SPI, uses its high bit to select the correct internal master key, K0 or K1, and runs that KDF calculation we talked about to generate the expected decryption key.
Calculates the key on the fly.
Exactly. This derived key, along with the received for, the ciphertext, and the authenticated but clear text data in PSP header, are fed into the AES GCM engine. It performs decryption and simultaneously recalculates the expected authentication tag.
Decrypts and rechecks the tag.
Right. An ICV check unit compares the recalculated tag with the ICV that came in the packet's trailer. If they match, the packet is authentic.
Success.
If it's authentic, a final merge step reassembles the original payload, now fully decrypted, and passes it, along with potentially the IV, SPI, and other info, up to the host software. If the ICV check fails, the packet is typically dropped or flagged as an error.
So, essentially the reverse process. Split, derive key, decrypt, authenticate, check tag, merge. With that key derivation being the really unique step compared to traditional IPsec offload.
That's the core scalability innovation on the receive side.
Okay. The specification also lists a number of requirements for NIC that implements PSP. Things it must provide. What are some key ones?
There are mandatory packet counters. You have to count packets that fail authentication and packets that fail encryption-decryption. Optional byte counters are recommended too.
Got to track the errors.
Yes. And they list specific statistical counters that should be provided for both receive, RX, and transmit, TX paths, total PSP packets, total PSP bytes, authentication failures, other kinds of error packets, bad packets, standard network monitoring stuff.
What about interacting with other NIC functions?
Importantly, if the NIC has any built-in forwarding rules that happen before PSP processing, like for specific low-latency traffic, there must be a way to configure overrides to allow certain traffic to bypass PSP encryption entirely if needed.
A bypass mechanism. Makes sense. And how should a NIC handle the packets themselves, both good and bad ones?
On the receive side, there needs to be an option configurable to pass the SPI, IV, and virtualization cookie, if present, up to the host software along with the decrypted data.
Give the host context.
And a clear flag indicating whether the decryption and authentication were successful. Also, crucially, a mechanism to capture packets that fail decryption or authentication for debugging.
Capture the failures.
Yeah, but with rate limiting so you don't flood the system if there's a major issue or attack.
Sensible. What about the transmit side? Sending packets.
A critical requirement. Packets that fail the encryption process for any reason must be dropped. You absolutely cannot allow sensitive plaintext data to leak out onto the network just because encryption failed.
No plain text leakage. Very important.
Also, similar to receive, there should be a mechanism to capture these transmit encryption failures for debugging, again with rate limiting. And an interesting option, allow the host software to pre-format most of the PSP packet itself and just send that down for the NIC to maybe add the IV and ICV.
Offload flexibility. Okay. Anything about reporting the health of the crypto system?
Yes. The NIC should provide status reporting. Things like a counter for how many times master keys have been generated and rotated, information on how heavily the transmit key resources are being utilized if the NIC manages transmit keys in tables, and the status of any relevant certifications, like its FIPS validation status.
Keep an eye on the crypto engine's health. Good. The spec also includes a section on defending against a specific attack, bad data injection, or misuse of credentials.
Yeah.
How does PSP help with that?
Okay, so the scenario is an attacker somehow gets valid PSP credentials, like an SPI and key derivation ability, maybe by compromising one endpoint, and tries to inject malicious data into a connection between other endpoints that happens to use the same SPI by chance, though unlikely with proper rotation.
Okay. How is that prevented?
Even though the receiving NIC might successfully decrypt the packet using its derived key, because the SPI matches one it knows, PSP provides two key pieces of information up to the host software. That flag indicating successful decryption authentication and the SPI value of the packet it just processed.
The SPI that was actually used.
Right. This allows the host software, like the TCP/IP stack, to maintain its own list of which SPIs are currently valid or approved for a specific socket or connection. It can then check the SPI provided by the NIC against its approved list.
So even if the NIC says, I decrypted this find using SPI number 12345, the software can say, wait, this connection is only supposed to be using SPI 98765 right now. Reject.
Exactly. It's a team effort. The NIC does the fast crypto and basic checks, but the host software provides the final layer of connection-specific validation using the SPI. It filters out packets that might be cryptographically valid but aren't actually for the intended connection context.
Color. A defense-in-depth approach using the SPI for context. Finally, there's an Appendix A that looks at different ways to manage the transmit keys. How keys are provided to the NIC for sending data.
Right, because sending requires the NIC to know the key beforehand, unlike receiving where it derives it.
What are the main methods discussed?
3 primary ways are outlined. First, you could store transmit keys in a small, very fast, on-chip memory table within the NIC. Good for a small number of flows needing top performance, maybe like encapsulated tunnels between fixed points.
Fast but small scale.
Second, you could have a larger secure associations database, maybe in RAM accessible to the NIC, handles a moderate number of flows, but there might be latency in setting up and tearing down entries, and it still has scalability limits based on the memory size.
More scale, maybe slower updates.
And the third method, which the spec seems to favor for large scale, is for the host software to provide the transmit key material directly to the NIC as part of the transmit descriptor of the instructions sent down with each packet or batch of packets to be sent.
Provide the key alongside the data.
Essentially, yes. This requires very little persistent storage on the NIC for transmit keys, avoiding the setup, teardown, overhead, and memory limitations of the other methods. It scales much better to millions of connections.
That sounds like the most scalable option, fitting with the rest of PSP's philosophy.
It does, though it requires the NIC's descriptor processing logic or DMA engine to be flexible enough to handle receiving and using this per-packet key information efficiently.
Makes sense. And the appendix wraps up by reiterating the scale needed, right?
Yeah, it emphasizes that realistic requirements for large data centers involve handling tens or hundreds of thousands of transmit SA updates, key changes per second, and supporting millions, potentially tens of millions, of concurrent transmit essays. That's the environment PSP is built for.
Okay, wow. We have taken a truly deep dive into Google's PSP specification. It's really clear. This isn't just, another encryption protocol off the shelf.
Not at all. It's a very carefully designed solution tailored specifically to the challenges of securing massive data centers efficiently. Scale and performance seem paramount.
What's fascinating to me is how they've tackled those fundamental problems. That receive-side key derivation.
It's particularly elegant, isn't it? A really clever way to overcome the traditional limitations of NEC hardware when you're dealing with just a mind-boggling number of secure connections.
Absolutely. And the benefits stack up.
Yeah.
The simpler design, the improved functionality like that UDP encapsulation trick for load balancing, the flexible crypt offset.
And of course, the significant increase in scalability. It all points to a protocol built very much for the future of data center networking, or at least Google's vision of it.
So what does this all mean for you listening in? Hopefully you now have a much clearer picture of why Google developed PSP and the innovative engineering that went into securing the massive amounts of data flowing through their infrastructure.
And maybe this raises an important question for you to think about. As data center architectures get even more distributed, maybe spanning multiple clouds or edge locations, and as security threats keep evolving, how might protocols like PSP need to adapt?
Good question. Or what are the potential implications, benefits, challenges for application performance, and even how developers write code as hardware-accelerated security protocols like PSP become more common? Does it change how you think about security?
Some really interesting points to consider there.
Definitely food for thought. And if you're eager to explore this in even greater detail, we highly recommend checking out the full open-source PSP architecture specification yourself. It's a real wealth of information on this kind of cutting-edge networking tech.
Absolutely. It's out there if you want to go even deeper.
Until our next deep dive, keep that curiosity going.